and then introduce John, who will give the lecture, right? So welcome everyone again. You're muted when you enter. If you have a question, which we encourage you to ask, you should ask it. Or if you don't want to use your own voice to do that, you can type it into chat and then I'll ask it for you. Or you can raise your hand if you want to be polite, and we'll call on you. But thank you for coming again. I hope you're all okay. I guess we had a bomb threat today at Brandeis, so you know, but I think it's all good now. So stay safe, everyone. But that aside, you know, it's exciting to introduce John Doye. He's agreed to stay up super late tonight to join us from Oxford, where he's a professor. He started out at Cambridge doing his PhD there, I guess also his bachelor's. And then he met Seth in Amsterdam during his postdoc in Don Frankel's lab. And he's been looking at how things assemble and how to understand their assembly the whole time, basically, right? And using different ways of sort of mechanisms of understanding it. So he's got an interesting thing that jumps onto a lot of ideas related to the IRG self-assembly. So it's a pleasure to have him here to speak with us.
Yeah, thanks a lot. I know quite a few of you already, but it's great to be able to talk to you. And hopefully some of the things I'll be talking about today will be kind of quite relevant to the kind of things you're doing in the center. So I'll just share my screen and see if that works. Okay. So can everybody see that now?
Perfect. Yeah, it's perfect.
Okay. Okay, great. So as John said, I've been kind of thinking about and working on self-assembly and ordering processes for a long time now. And when I sort of came to Oxford, I started to think about DNA and DNA assembly in various forms. And what I'm particularly concentrating on today is the assembly of DNA origami into larger structures rather than the assembly of the individual origamis. And I'm going to kind of look at 3 examples of DNA related. You see one isn't 2 DNA yet. Hopefully it'll be more DNA related in the future. I put this first one in about self-limited oligomerization because that's very relevant to the center, and how stress buildup can lead to finite size. Another one which is very related to Brandeis and the work of Zonomir is looking at cholesteric liquid crystals of DNA origamis and what the origins of their chiral behavior are. And the last thing, DNA kind of related, is thinking about how to make icosahedral quasicrystals. So this is very new stuff. And the last thing, if I've got time, I might talk about is some work on programmed liquid phase separation in cells using protein complexes as the kind of units we program. Okay. So most of you know about DNA origami and structural DNA nanotechnology. This is a kind of timeline for some things in DNA nanotechnology. I got interested in it about 2006. I applied for a job in Oxford, and one of the people in Oxford physics is a guy called Andrew Turberfield, who made this tetrahedron. And I think on the day of my interview in Oxford, I went to see Andrew just to kind of get an idea for some of the things he was doing. I saw this tetrahedral assembly and thought that looks really kind of interesting self-assembly thing. And while I was there, his postdoc knocked on his door, put his head around the door and said, "It's out." Had a copy of the Nature with this DNA smiley face on the cover from Paul Rodman's kind of landmark paper on DNA origami. So that's kind of started my journey into DNA origami as a kind of, and thinking about self-assembly problems with DNA. And how all these kind of structural DNA nanotechnology things work in some sense. It just uses the programmability of the DNA sequence and the specificity of Watson-Crick base pairing to design the free energy global minimum of the system. So if you look at this double crossover tile over here, if you look at this red strand, this section is complementary to this part, this blue section, but rather than as in a normal DNA duplex, where you just have 2 completely complementary strands, here you've got this red molecule is complementary to bits of different strands in different regions. So what's to bind to this blue bit, then this part of the yellow strand, then another part of the yellow strand, and finally to this blue bit here. So all you're doing is using the sequence to design the free energy global minimum. And how most of these assembly processes work is you take all the mixture of strands at high temperature where nothing wants to bind. As you cool it down, there's a point at which these things become the only thing stable with respect to the single strands, and hopefully the things can assemble at that point. And yeah, we're going to focus on the DNA origami today, where you have one long scaffold strand which comes from a viral DNA, normally about 7,000 bases nucleotides long, and it's bound together by the same principle as this double crossover tile, but with lots of small strands which bind specifically to places on the scaffold. Okay. So I was interested, can we start to think about the assembly of this tetrahedron? And with simulations, can we begin to understand that? When we came to think about that, we wanted a coarse-grained model of DNA to do that, because clearly with these diffusional processes causing the self-assembly, they'd be much too slow to do with all atom simulations. But there wasn't any kind of good enough DNA coarse-grained model on the market. So one of our students, Tom Aldridge, I've done most of this work on DNA with another professor here, Ard Lewis, who we kind of both came to Oxford from Cambridge at the same time. So we just started to design our own model, and this basic nucleotide of this model, which we came to call OXDNA, basic unit of this model is a single nucleotide, which has sites for the backbone and the base, and then a relatively complex series of interactions between them to capture the orientational dependence of various types of interactions. And I've kind of labeled the types of interactions we have a simple backbone interaction. The bases along the chain want to stack on top of each other, and so they want to do that in a kind of coplanar way, so it has an orientational dependence. We also have those bases which are complementary, can form hydrogen bonding interactions associated with the Watson-Crick base pairing. And then we also have the bases can also interact across the duplex in that diagonal way. This was what's called cross stacking. And the final stacking interaction in there is, which is slightly different, is what we call coaxial stacking, where you get stacking between two bases which are not adjacent along the chain. And this is actually can be quite relevant to some of the methods to assemble DNA origamis into larger structures. And the final interactions are just excluded volume and electrostatics associated with the backbone.
So John, have you done anything to better parameterize the coaxial stacking, or is it?
I'll come to that, yeah. Okay. You may have discovered some of the problems for what you might be interested in.
Well, you warned us, yeah.
I did, yeah, I forewarned you, okay, yeah. So the issue with the coaxial stacking is that actually there's not that much data to parameterize it. So our parameterization approach has basically been to fit to experimental data. There's a wealth of experimental data on DNA thermodynamics, hybridization thermodynamics, and the kind of all the single molecule work, mechanics work, has given good information about mechanical properties of single-stranded DNA and double-stranded DNA. But yeah, the coaxial stacking interaction has been less data on it, and the kind of value for the strength of it we use in the model is a bit of at the time when we created the OXDNA2 model, it was a bit of a balance between fitting to two sets of data, which seemed to be not consistent with each other, at least as we kind of modeled them in the try to capture in the model. And so we had to choose intermediate value, which is probably actually too low for some things, but we'll come back to that. And so this is the original version of the model, which had a symmetric helix. And then as we wanted to use it for DNA origami and things, we tuned a few of the properties to make them more accurate, which we hadn't really kind of considered when we created the first model, introduced major and minor grooving and a few extra things. So that's the kind of model we always use, and one must use this kind of second generation model for DNA origami. The first generation model won't work well because the pitch is not exactly the right value. And fortunately for us, this model works unreasonably well, much better than we'd ever hoped it might do. And that's to a large part due to Tom Aldridge, who was a spectacular PhD student who started this program. But the model is now available for any to download. It's on SourceForge. We've got a GPU version so we can cope with very large systems. The largest systems I've done, I think, is about, I'll show you later, is about 500,000 nucleotides. I think people have done larger systems than that. It's also in LAMPs, but only in, I think, at the moment just in a parallel CPU version. Also, as it's become more well used, there's kind of developed infrastructure around the code to be compatible with DNA nanotechnology design tools like CAD Nano and others. And so, for example, this is one thing that can be used, OXDNA, which converts between different formats. So that's quite a useful thing. And I would particularly highlight this new tool that came from Peter's group in Arizona State called OXView, which is a kind of browser-based visualizer, but also a manipulator. So you can actually start changing your structure in OXView and pulling things together. So it's actually a very powerful tool and made a lot of things associated with DNA origami much easier to do. Here's just an example of 4 origami tiles on that kind of surface that I've just happened to have loaded in. And it is becoming increasingly used by both the DNA biophysics community and DNA nanotechnology community. The number of publications is kind of gradually creeping up as we go through time. Okay, so how good is it at modeling DNA origami? What I'm showing here is a comparison between an experimental cryo-electron microscopy structure from Hendrik Dietz's group. It's kind of an asymmetric structure, kind of a pointer. And here is the representation in OXDNA with unfortunate color scheme, but let's ignore the color scheme for now. But the key feature of it is actually it captures quite a lot of the structural detail of the DNA origamis in pretty well. So if we look at the RMSD between our structure and the experimental structure, it's under a nanometer, and the estimated experimental resolution on these things is about similar. But if you're a little bit eagle-eyed, you might notice, well, this is a square lattice of helices, square lattice origami, and there's a slight twist in this origami. And you do see a slight twist in our one, but you kind of, if you look at that kind of surface and this kind of surface, you probably notice that this one's a bit more twisted than our one. And that's kind of a slightly open question. What's the real twist of DNA origamis, and is OXDNA capturing it? It's not a big deal for something which is quite rigid like this, but for 6 helix bundles and other things, it can be more of a question. But one thing to bear in mind actually is not just is OXDNA accurate, but are these cryo-electron microscopy structures really realistic of the room temperature structure? One of the things about DNA is the pitch of DNA changes slightly as a function of temperature. And as you kind of freeze your origami, it's not quite clear in cryo-electron microscopy what the effective temperature you've effectively sampled from your system. And it may be that actually this is more twisted because the pitch of the DNA has changed as you've changed the temperature, and it's been able to twist the structure a little bit from its room temperature form before it's kind of got frozen in. So that's kind of, I think, an open question. But basic summary of this is that OXDNA does give a very good picture of the origami structures. How about mechanics? I know you guys are quite interested in mechanical properties of origami assemblies. So we've looked at 6 helix bundles that are just rods of 6 helices bound together in an origami, or perhaps in with single stranded systems. But these are very stiff, much stiffer than a DNA duplex. So DNA duplex has a persistence length of about 50 nanometers, 150 base pairs, whereas the persistence lengths of these origami rods are of order of microns. And you see the kind of comparison between OXDNA and experiment. It's reasonable, but there's a slight larger persistence length for OXDNA. This is the variance is just different types of 6 helix bundles we've looked at. And then there's also been some really nice experimental work by the Lidl group where they've twisted a 6 helix bundle and measured its twist modulus, and that's actually probably a bit better. The kind of OXDNA kind of model of that. It's still a bit high, and you can say, what's the reason for this? This is just that OXDNA doesn't capture things perfectly, and it could well be that. But also the other thing to remember is that when we are studying these systems, we've kind of created perfect origamis which are completely self-assembled correctly, and there are no kind of defective strands in there, which won't always be the case for the real systems. And then a reason why the OXDNA model might give a bit higher stiffness as well is when we were fitting the model to the mechanical properties of DNA, we were more concerned with getting the twist modulus of double-stranded DNA and the persistence length of double-stranded DNA correct. And we couldn't do that and also get the stretch modulus correct. So the stretch modulus of OXDNA is about 2-ish times too large. But when you come to bending a 6-helix bundle, what you're actually doing, as well as bending the actual individual helices, the helices on the outside of the bend are being a bit stretched, and the helices on the inside of the bend are being a bit compressed. So it may be that the fact that we've got our extensional modulus a bit high may be one of the reasons why these numbers are a little bit high. But the basic, again, the basic thing is that actually it's doing a pretty good job of capturing the mechanics of these systems. And if you look at comparative mechanics rather than absolute numbers, I'd expect it to do very well. And before I get on to the case studies, this is just one kind of last example to show some of the caveats with OXDNA, and this is about the coaxial stacking interaction. So Hendrik Dietz has pioneered using blunt-ended stacking, so the stacking between two kind of ends of two helices to drive assembly processes. And this can be between origamis. He's got some, as you know, they've been some beautiful work on that, and you guys have carried that on. Here we've got one of the original systems is this switch, which has kind of two origami arms with a kind of which can freely rotate with respect to each other, and the arms have got these kind of sections which are shape complementary and can bind to each other, and then that can drive it into the closed form. And Hendrik showed this really nicely. You can drive it between the closed and open form by changing, for example, the salt or the temperature to change the strength of the blunt-ended stacking interactions between the kind of ends of the red and blue helices. And so this is that structure in its closed form in OXDNA, where we've highlighted these different regions, red and blue regions. But one of the issues is if we look at this structure, we pull it together to get it to assemble into the structure, and then if we let it go, it will go into the open form, even at the kind of salt concentrations one would expect it to be in the closed form. And what one needs to do to get it to stay in the closed form is increase the coaxial stacking interaction strength a little bit to get to hold there. And so that kind of indicates that to capture this blunt-ended stacking, the kind of interaction is probably a bit too weak. But that can be changed just in the input file, so that's something that can easily be changed by hand. Another aspect of it is the orientational dependence of the stacking. So in the helix, stacking interactions in the helix have an orientational dependence kind of with the twist of the bases with respect to each other. And this is actually relevant for this system, although I don't think Hendrik realized it. So this is the kind of designed isomer of the system. But actually you can take this rod and rotate it by 180 degrees, and it's not clear that it's going to be any less stable in its open form in that way. And you still have this shape complementarity after you've rotated it by 180 degrees in terms of the overall shape, and they can then bind into close. But one of the differences is, because this is a chiral object, how the bases come together at the kind of interface of the blunt-ended stacking is different. So this is a designed isomer where the helicity it just carries on like a normal double helix in the how they're arranged, and that comes naturally out how they're designed in the CAD nanofile. If you look at the Ternert isomer, the kind of twist angle between the bases in this coaxial blunt-ended stacking junction is slightly different. And as it happened, we've chosen our coaxial stacking orientational dependence to be pretty similar to that in the of our stacking interaction, which kind of favors it has stronger stacking when it kind of looks like the stacking in the double helix. So this isomer is actually more stable in OXDNA than this isomer. So that might be another potential issue with the coaxial stacking. But as I say, most times as things are designed in CAD Nano, you tend to have kind of just translated the bits that lock into each other up and down in your CAD Nano diagram, which actually means I have the kind of are in registry in terms of their twist angle. But interestingly, in the experiments, I think they put two fluorophores, say, on this end and this end to measure if it closed. If it actually had assembled into the other isomer, you couldn't actually see, the fret wouldn't actually have picked up whether it was opening or closing. So they were probably only seeing the closing of this isomer, and there might be no signal if isomer B was closing or not, as it happened. And there's no particular reason why it must assemble with this rod in this orientation rather than with 180 degrees rotation. So it's a little bit of a kind of technical thing, but I thought it might be of interest to you, given that you're thinking of using coax blunt-ended stacking a lot, and if you're interested in modeling those kind of things. But the simple solution in the modeling, in some sense, is just to turn the interaction strength up, and it will hold in the correct place.
John, can I just interrupt for a second? It wasn't clear to me. Did you say that Hendrik did not measure the two different fluorophores? He didn't use different fluorophores, or used the same one, so he couldn't tell?
So I think he put, say for example, I think you put fluorophore here and here in the kind of designed isomer. So when they close, you get a fret signal. But if you're in the other isomer, it's on the other end, and when it closes, they haven't come close to each other. So it wouldn't have seen if the other isomer was present and opening and closing, I don't think it would have given a signal in their fret. Because in the open form and the closed form, the fluorophores will be too far away to give you the fret signal.
Yeah, but
so
I mean,
you've been looking at half the population in the experiments.
But I mean, you could design it so that, I mean, it's simple enough to design so that you would be, right?
Yeah, of course, you can just put fluorophore here and here, which wouldn't detect the closing of this one, but would detect the closing of the other one, and it would also see if they had transition points which were slightly at different salt or something like this. Because I think things like the orientational dependence of these interactions, and a lot about the coaxial stacking interactions, are a bit of a there's not that much data out there, but you could do design experiments to do that, which would be interesting to us, but perhaps not to more generally. If it does what it meant to do, then.
But you're just saying he did not do that. Those experiments have not been done, you're saying?
No, I think they just assumed it would form into this isomer and didn't think about I haven't chatted to him about it, actually. I did mention it to him, but by email.
Thank you.
But okay, so our kind of first case study, and this is a kind of self-limited oligomerization, and this is work with experiments by the group of Lawrence Lee at the University of New South Wales with these kind of postdoc or PhD student Jonathan Berengut. And here's the kind of basic unit for which we'll polymerize in a one-dimensional fashion. And you have these two units A and C, which are kind of equivalent, and this unit B in the middle, and they're attached to each other by these helices, but you can get kind of free motion of these helices. So the top and bottom can move side to side with respect to the middle. And then what he's designed is that the blue interfaces on this unit in the center can have these complementary sticky ends. They're actually two base pairs, and you can choose how many you have, from 0 to 24. If you have 0, it can only bind by blunt-ended stacking. And so the idea is that it will polymerize through interactions between this B domain. But on the A and C domains, you've added poly T tails of different lengths, of a length you can choose, and these will have an entropic repulsion between each other. So that as you bring two of these together, like into this structure, these poly T tails will take up room, and they'll be pushed aside. As you polymerize it, they have to be pushed further and further aside, and the strain will build up. And at a certain point, you imagine the strain is so large that another one coming in, it would be unfavorable for another unit to come in.
How are the A's and C's able to move side to side? Like what is moving?
So I can't remember exactly how many turns these bits are, but they can move. So there'll be an entropy loss as well when they become constrained in the structure, as well as the fact that you've got these poly T's pushing together. But I'll show you distributions of that kind of motion in a minute. And so that's the basic idea. You have a kind of nonlinear. The hope is you have nonlinear strain build up as the system polymerizes, and that will naturally cause it to stop at a certain size. And you can control the kind of repulsions between the poly T tails, and you can control the interaction strength between the B box by how many sticky ends you have. And so this is what it kind of looks like in OXDNA. As you bring them together, you get this polymer, and here is this kind of side-to-side motion distribution. This is not for one, but for two, and you see that the one's been pushed to the right, one's been pushed to the left, of course, in this kind of example. This has been pushed that way and that's been pushed that way. And these are still quite wide distributions at this point. They've been probably a little bit narrower than for the monomer. But as you bind more and more of these, at the ends of the chain, the displacements become more extreme, so costing you more free energy, and the distributions come narrower as they're kind of compressed together by the stress in the system.
How are you simulating these? Are you putting them in place and then doing some kind of umbrella sampling?
No, so this is just, we've pulled them together artificially to create the structures, got them to bind. Once they've bound, just watching. So we're not looking at the polymerization, but looking just at the structurally characterizing the different oligomers. And so we just do a brute force simulation of this, I think that's a 9mer, and then measuring the distributions of the different blocks with respect to the center for each of the up and lower blocks on these 9 origamis. And so, yeah, you get them being pushed further apart. And if you look at the kind of this delta X, perhaps unsurprisingly, you have this fairly linear pattern. The middle ones roughly in the central position. These ones are pushed to the left, these ones are pushed to the right. That's all we're just seeing there. But the slope does change as you go to larger ones as they come more compressed, and it's costing more and more they're resisting being pushed. The end ones are resisting being pushed further and further apart because of the stress. Okay, so that's what the simulations look like, and what this effectively means.
We have a question from the audience that I will relay. It's about the model for the Higgs 6-bundle helix. If there's a twist modulus that matches nicely, how does it go wrong for the stretch modulus? Is it due to the overestimation of some kinds of interactions?
So for the, okay, so that's a kind of interesting question. Why can't the OXDNA model get the all the 3 kind of modular twist, bend, and stretch modulus of a double strand correct? And I'm not totally sure. So people often talk about a DNA duplex as an elastic rod, but it's not quite. So if you back out the Young's modulus from its bend modulus and then to estimate the stretch modulus from there, they aren't too far off, but they don't agree. And certainly for OXDNA, if we do that kind of calculation, they are different. So it's not just behaving like a uniform elastic rod in OXDNA. I'm also wondering, we've got a kind of implicit solvent model. Does the solvation affect things as well in some sense? When you bend DNA, you're not just kind of bending the duplex, but you're doing something to the water outside. Does that provide any resistance, which we haven't got in our model? I don't know. So it's a kind of interesting fundamental question of why, why can't we capture all 3 those 3 moduli in our model? I don't know. But we prioritize bend and twist because that's the things we thought would be most relevant to lots of the kind of DNA physics which we were planning to think about. Okay. So we do see this nonlinear stress buildup, and this kind of similar things are seen in the experiments. Here it's these kind of electron microscopy pictures of different oligomers. So they've kind of put some together with different numbers of monomers. You do see some of the more subtle features we saw in the origamis, which I didn't point out, that they are actually slightly canted rather than being actually parallel to each other. And you kind of see some of those features. And these things do try to find other means of stress release rather than just moving the block side to side. So here, if it's canted like that, they kind of slightly fit into each other, because that then reduces the stress in the system. If it pays something for canting it like that, but then it doesn't have to displace them so far. But the kind of what they see is kind of what you expect. On this, going down here, you're increasing the repulsions between the blocks. Here, you're increasing the attractions between the center blocks. And so as the attractions between center blocks, you get a increasing length, average length, and as you increase the repulsions, the length decreases. So the kind of basic physics of what's happening in the system kind of makes sense and is kind of in agreement with the simulations. One thing you could ask is, as it's polymerizing, you kind of think about the on-off rates of these blocks. We'd probably think that actually it's the on rates which are most affected by the stress in some sense, because as one of these blocks has got to come in, it's got to get into a very entropically unlikely, perhaps slightly enthalpically unlikely configuration with the two blocks displaced away from the center, and that's going to cost you some free energy. And so we think it's mainly in the on rate that this stress buildup is affecting the kinetics associated with underlying it.
Okay. Is it, do you see evidence or suggestion that it's going to escape self-limitation? You know, if you make the attraction strong enough, then it will just...
So if we, it's an interesting question. I think, so if you just have the 1T thing, it, even with the kind of maximum strength is self-limited still. You can't have the kind of 0T control, because then you'll just get blunt-ended stacking between the blocks. So they have a control where they make these blocks smaller either side, and you just have, so you have no repulsions between the outer blocks, and they just polymerize in an unusual kind of fashion. But the minimal system with 1T is still self-limited. What we do see kind of in our data, this is for the 3T system. If we put 6T system in there particularly, then it does find other mechanisms of getting rid of the stress as well as just displacement of the center blocks. They can kind of twist and void each other and reset the displacement a bit. So as the stresses get larger, it will try to find other means, or it's more likely to find other means of escaping the stress rather than just this one-dimensional motion of the blocks at the top and bottom. But they don't.
It seems like there should be some interaction strength at which it would just be favorable to, you know, whatever it has to do, it'll do it.
Well, I'm not sure perhaps if you sufficiently, I suppose the kind of at a certain point, it just, yeah, you can just compress these sufficiently that you don't, yeah.
Right. Exactly, yeah.
Yeah.
Maybe a very, very high limit, which is interesting.
Yeah, so what we can't do really, we can't really do the proper thermodynamics we're looking at structural characterization in the OXDNA, and in the experiments they are only seeing short ones.
Mm-hmm.
Yeah. So what they perhaps could have done, increase the interaction strength, is made it, rather than 2 base pairs, made it longer. So
hey, maybe following on that question, I guess you can't do thermodynamics, but is it possible in OXDNA to look at, we tried to do some version of this, the, I don't know, energy increase in as a function of size, the internal energy of a brick defined in some way,
yeah,
not maybe internal free energy of the brick.
Yeah, kind of. So what we've done some kind of one-dimensional models of this, where we've taken say things like using the data on the monomer to look at the kind of distributions of the top and bottom blocks, say in the one-dimensional motion, and that gives you a kind of pseudo-harmonic free energy as a function of that displacement, which we've characterized from the monomer, and then we can put in a one-dimensional model to look at those kind of things. And then we've characterized the repulsions between the blocks with different T's and things. So we've tried to come up with a kind of using the monomer properties to come up with a kind of model, but we can't directly measure it in the actual OXDNA simulations. And so what we kind of see is, if the repulsions between the blocks were hard, we'd kind of get a cubic build up in the free energy with the number of particles. But as the repulsion is a bit soft, it's kind of in between quadratic and cubic, roughly. But, okay, so the next little case study is on the cholesteric liquid crystals. So a cholesteric liquid crystal is basically a nematic liquid crystal of molecules or particles which are chiral, and the chirality causes the nematic director, the direction in which the molecules are aligned, to rotate as you pass through the system in one direction. So in this example, you kind of got these little ellipses to show you the molecules or the particles, and their directional orientation kind of goes through a 360-degree rotation between the top and bottom, and that's what we call the pitch of the cholesteric. And this leads to these classical kind of banded patterns in cholesterics. To try to model the properties of cholesteric liquid crystals is actually very difficult by kind of theory and simulations. The main big problem is this pitch is typically a long length scale, many particle diameters. And so if you want to simulate the system, you'd have enormous systems. So you have a kind of, the phase is weakly chiral. So this is only a slowly varying rotation. And the other problem is that it's due to the chirality of the particles. And so to capture the chirality, you might need a very detailed picture of the particles to capture that chirality. So you've got really long length scales, but where you need to know the details. So this is the, for example, FD virus, and this is the chirality of the surface of FD virus. To capture this, but yet like these kind of length scales is very impossible in simulations. So I won't go into the details, but we used a classical density functional theory to do this, where we've used, we're going to look at DNA origamis, cholesteric phase of DNA origamis, where we used OXDNA to potential to look at the virial integrals, the kind of pair integrals between two randomly oriented DNA origamis. But that's still computationally very challenging, but I won't go to the details of that. Okay, and one simple argument to explain why a particular system might show a right or left-handed phase. So the rotation can be in a right-handed sense or left-handed sense as you go through the system. And if you kind of imagine two kind of things which look a bit like screws with grooves in them, then if the angle of the thread of the system with respect to the kind of perpendicular to the axis of the particles is less than 45, then to get the grooves to kind of lock into each other of your screw, then you typically have to have a right-handed twist between the particles. If you have right-handed screws, these are right-handed screws. So alpha less than 45, you have the same handedness in the particle and the phase you'd expect. Whereas if you have quite weakly twisted systems with say alpha greater than 45, then the opposite's the case, and you have you're expecting the most favorable interaction between two particles to be with a left-handed twist. So that's the basic idea. And as you probably, many of you have seen, these are, we're going to think about the experiments of Zvonimir on these twisted 6-helix bundles. We've got some right twisted helix bundles and some left twisted helix bundles. An interesting question is that actually, is this, say this one really straight, or is this slightly twisted? I think it's still open what's the case there. But they are very long and stiff particles. And these are the Zvonomir's experimental results. And particularly he found that the most left-handed one had a left-handed pitch. What we've plotted here is 2 pi over the pitch, the kind of inverse pitch. And negative is left-handed and positive is right-handed. So 0 would correspond to something that is achiral. So the left-handed one has a left-handed pitch, and the right-handed one has a, most right-handed one has a right-handed pitch to the cholesteric. So this is a bit surprising in a way, because if we look at these particles, they're weakly twisted, and so alpha is not far, is kind of probably 85 degrees or something, and so we expect them to be in the regime where they want to be have the opposite chirality to their screw. So a right-handed one will want to be left-handed, and a left-handed particle will want to have a right-handed phase. But what we instead find is that they basically want to be isochiral. The twist of the particle matches the twist of the phase. So that's a bit of mystery. So we tried to start to look at this with our density functional theory approach using OXDNA to model the origamis. And so here's the experiment again. And this is what we found. I've used the same color scheme when we just looked at kind of rigid rods. So we've just taken these rigid structures, assume they're rigid for the moment. And what we see is the right-handed one, the purple, is left-handed, and the left-handed one is right-handed. So that agrees with this basic rule here, but is in total opposite to experiment. So it kind of confirms our idea that we thought they should be opposite chirality. It kind of makes sense out of the twist in the origamis. This is actually just with the sterics. If we turn on electrostatics as well, then actually what happens, you see the same trends, but the one over the pitch comes even smaller, the chirality comes even less. So the pitches are really, really long. They're only very weakly chiral. And if you look at these numbers anyway, they're much smaller than the experimental numbers. So what we see, if we just take into account the surface chirality of these particles, assuming they're perfectly rigid, is that unsurprisingly, this looks like a rod, a kind of a cylinder, rather than something that just has high chirality. You have to look at the surface very closely to see that actually it's got the grooving between the helices will give you a slightly chiral surface. If you turn electrostatics on and they repel each other more, they feel that chirality even less. So these rods by themselves aren't inherently very chiral. So that's why we're seeing such weak chiralities, large pitches, and it's the opposite handedness to we're seeing experiment. But what we can do is, rather than in our viral integrals use these rigid structures, we can take ensemble structures from our simulations of these particles. And when we do that, the situation is totally reversed. So what we see is that the left-handed one is now left-handed, the right-handed one is now right-handed. So we reverse the trend, and the phase chirality of predicted is much closer to the experimental kind of numbers. So they're much more chiral. We also now notice that when we turn the chirality, I think their solid lines are just with the steric interactions. We put electrostatics on, and it doesn't make too much difference to the phase chiralities. It reduces a little bit, but not very much. So what's going on? What it must be the case is the chirality in the system is not driven by the chiral surface of the particles, but their chiral thermal fluctuations. Once we put the thermal fluctuations that come out of the OXDNA model, then we see the correct behavior. So we can start to characterize that a bit. And what we've done here is basically kind of look at some Fourier-like analysis of the displacements of the center line of our particles. And what we see, and we've developed to look at how helical they are, this kind of measure here. If you have a perfect helix on a certain inverse length scale, you'll get a value of 1. So a perfect helix would be 1, where +1 would be right-handed and -1 would be left-handed. So if we look at these, the ensemble structures that our origamis take up, so the purple one is the the right-handed. So the right-handed one now has a negative value for our helicity measure on long length scales. So that's saying that it looks like a left-handed kind of helix in its fluctuations, whereas the left-handed ones show right-handed helicity. And you can in these two pictures here, we've picked configurations which show that. If you look carefully, this is left-handed in the actual twist of the origami, but you can see it's forming a right-handed helical helix. So you're seeing these helical fluctuations in these systems, and that is the origin. These chiral fluctuations are the origin of we believe, and OXDNA suggests, of the chiral phase behavior of these systems. But you could say, why are the left-handed ones having right helical fluctuations on average, and the left-twisted ones having right helical fluctuations? And where this comes from is the actual internal mechanics of the origamis. So these helix bundles are based on this hexagonal lattice of helices, and the distance between junctions in this kind of perfect regular system is 7 base pairs, and the pitch of DNA is virtually exact, such that gives you an angle of 240, 2/3 of rotation. but how they program in the twist into these particles. For example, if you had an extra base pair between these junctions, so rather than 7 base pairs, it's 8 base pairs, then the twist in the system between these two junctions must be slightly less. You're going to have an undertwist in your individual helices. And this is what we see here. We're looking at the twist, the change in the twist effectively in the different systems. So the right-handed, if it's untwisted, this would be the undertwist in the individual DNA helices. But of course, it doesn't want to be undertwisted, so it will push against these junctions and cause a torque on these junctions. And that will, if you have these kind of blue sections where you have these insertions, these extra bases at the same place, this is going to cause the whole system to right twist. And this is going to reduce the undertwist in the individual helices. So rather than going from untwisted rod to that to be straight but twisted, then this undertwist goes down. Then when we consider thermal fluctuations of the system, if you had a topologically closed double-stranded DNA, you have the linking number, which is topological invariant. And so these systems aren't topologically closed, but the helices in these origamis are constrained by the junctions in the system. And if you have a system where you have undertwist in the straights in the individual helices, then what could happen to reduce the stress in those individual helices, if you have a negative writhe, then that will reduce the undertwist in the system, because if this linking number difference is roughly conserved, won't be perfectly, but you can see how a negative writhe will have the effect of reducing the twist and the undertwist in the system. So when we look at a thermalized ensemble of configurations, the extra twist in the individual helices is less than you would expect in the twisted but straight ground state, and it develops a negative writhe, a left-handed writhe. So we're seeing that a right-twisted origami has a left-handed writhe to it. It has kind of left-handed helices in its shape. And the opposite is the case of left-handed state. The individual helices are over-twisted, and this causes a preference for the system to have a right-handed writhe to it. And so the origins of these chiral fluctuations are in the chiral mechanics of the individual origamis and how the twist in the origamis is programmed into the system. So I think it not only can explain the our OXDNA results, not only are consistent with experiment, but I think they can understand the origins of these writhe fluctuations of a preferred handedness. Okay, just check that. Okay, I better be quick. I probably haven't got time for the liquid-liquid phase separation, I think. So the last thing I want to look at is programming patchy particles, and we're going to see if we can realize those patchy particles with origamis to form complex crystals, or to form icosahedral quasicrystals. First, we worked out how we can make complex crystals with patchy particles, and basically in these patchy particles we have an interaction where if the two patches on the surface of the particles point at each other, you have a strong interaction. In this system we also have a torsional interaction which controls their relative twist about that bond. So in these systems we have so this, for example, this clathrate structure, there are 4 unique environments in the system, and we have a patchy particle to represent each of those unique environments. So this system of 4 patchy particles assembles into this clathrate, and we've chosen the geometry of the patches and the geometry of the torsions to stabilize the structure, and these easily assemble. So it's not too unexpected. If you program the structure of the crystal into each of the particles, and you have a unique type of particle for each particle environment, then it should work. But how can we then move this further to think about how to form an icosahedral quasicrystal? Icosahedral quasicrystals have icosahedral symmetry, but orientational symmetry, but no long-range periodic order. They've been seen in experiment for metallic systems, but no other systems. In simulations, there's this recent work by Sharon Glotzer's group where they use potential with multiple minima, and they found this isotropic potential which generates this icosahedral quasicrystal. There've also been work where they've used softer, ultra soft potentials which don't have hard cores. And in those systems, you can show that if you basically have two length scales in your system, in your kind of potential or its Fourier transform, and these length scales the ratio of these two length scales is the golden mean, then you can favor the an icosahedral quasicrystal. So in this system, it's not so straightforward to do that analysis because of the hard core, but basically you've got these multiple minima in the system, and they've tuned these minima until they've seen these icosahedral quasicrystals form. So it's the two length scales and the potential which are driving this. But these potentials are complex as a function of the radial distance and be hard to realize. But you do see these beautiful fivefold symmetric patterns. One of the curiosities about this in some sense is, although it has beautiful global long-range orientation order, at a local level it's quite disordered. So if you look at the, you only have, it's a monotonic one component system, but if you look at the coordination number distribution of these systems, it's quite wide. So the particles aren't in a wide range of environments in terms of their coordination number, for example. So there's actually quite a lot of local disorder, even though this kind of really kind of perfect long-range icosahedral orientation order. So how are we going to go about programming this into patchy particles? So first of all, we want a reference structure to work out what the potential local environments in this system are. And you can do this by what's called a cut and project method, where you can generate icosahedral quasicrystals by projecting a 6-dimensional lattice, a cubic lattice. In this instance, we're going to think about body-centered cubic lattice, project it onto a 3-dimensional space, which is a cut through that 6-dimensional lattice. And if that cut is at the right angle, and the angle is related to the golden mean, then you get an icosahedral quasicrystal. And so this is an ideal quasicrystal produced by this cut and project method from the 6D body-centered lattice. And we can start to look at the different local environments in the system. We're not looking at the unique environments, which are, but just their local environments in terms of the local orientations of their connections to particles surrounding them. And in that case, we see these 3, 5, 7, 10, 11 different local geometries of the bonds around the system. What we can also do by the cut and project method is, rather than cutting this 6D lattice at a rational angle, if we do it at a rational angle, then you can get an approx, which is quite close to the plane for which you get the icosahedral quasicrystal. Then you can get a rational approximant. So this is called the 3/2 rational approximant, where 3/2 is approximation to the golden mean. And this is what this periodic crystal looks like. In both these systems, we see this kind of cluster where you have this icosahedral cluster, where at the center you have this triacontrahedra, and then these particles around them. If we look at the local environments in this periodic approximant, we again see very similar local environments. All the ones shaded in pink are the ones that occur both in the approximant. But even if we just say, okay, we're going to have particles for each of these 11 environments, it's a very cumbersome system. So what we've done, rather than say, actually, we want a model which will be fully bonded in our target structure, say the icosahedral quasicrystal, we just take these 5 classes and create a patchy particle for the most bonded one in each class. So one for this class, that's that blue particle, one for that yellow class, one for this class, one for this class, and one for this class. And if they don't use all their patchy interactions, so be it. Of course, one might wonder if you have these particles which are not going to be fully bonded in the final structure, would there be alternative structures which are more stable? So we've started with these 5 patchy particles, put them in a box, cooled it down, and see what happens. And this is what happens. We get these clusters growing. Here's a background gas, effectively, low density fluid, and we've got this particle growing. Here we've taken a cut through that particle and coloured them by the colours here. And if one was to look very carefully at that, you can see these triacontrahedra, and they're all oriented in the same way. Their 5-fold axis is all out of the plane. What we've drawn here is a bond orientation order diagram, which basically looks at the directions of the bonds in the system and projects them onto a sphere. And we've done a 2D projection of that. and you can see clear icosahedral order in that bond orientation order diagram, where the bonds are oriented along the 5-fold, 2-fold, and 3-fold axes. If we take the diffraction pattern, we see this perfect 5-fold diffraction pattern that you'd expect, and you have the ratio of the distances of the spots from the center follows powers of the golden mean, which is kind of characteristic of these icosahedral quasicrystal. Were we just lucky? We did the same thing again, but for what's called a primitive quasicrystal, where we're projecting from a primitive 6-dimensional lattice. In this example, the number of environments is actually larger, but we found that we had these clusters in there, icosahedral clusters, and we were just beginning to model these systems, and worked out we needed 3 particles to model these clusters. We just checked that everything was working, so they would assemble these clusters. And what we actually saw, without the other particles, environments in the system, that actually just with these 3 particle types, we formed this beautiful quasicrystal again. This is a kind of projection, and you can clearly see the 5-fold order in this. It gives a perfect diffraction 5-fold diffraction pattern again. Yeah. But in both these systems, what we see is, as kind of expected from our design approach, that actually the particles aren't fully bonded. This is the fraction of the particles that have no kind of missing bonds, and it varies between about 60 and 80%, depending on the quasicrystals and the approximate. And you have a certain fraction of these dangling bonds. But you could ask, okay, these are relatively simple systems, 3 particles, 5 particles, can we make the system simpler? And the answer is actually yes. In each case, we can reduce the system down to 2 particles, which will still form an icosahedral quasicrystal. In this example, we first saw that these yellow and purple particles weren't actually incorporated very much into the quasicrystal, so we just got rid of them, and that's still, this 3-particle system still formed this quasicrystal. We also, if you have a look at this trio contahedra, you have bonds between the green particles and the bonds between the green and reds. The green particles form a dodecahedron. We thought, okay, what happens if we just get rid of the red particles and just have green and blue particles? So you have 2 types of tetrahedral particle, and again, this forms an icosahedral quasicrystal. In the other system, we had this red dodecahedron in the center, surrounded by these green and blue particles. You can actually get rid of the red particles. You don't need these central particles in these clusters, and this system again will form a icosahedral quasicrystal. In all the models so far, we've included torsional interactions in the interactions. And if you take them out of this system, as you could probably guess, there are lots of different polymorphs for tetrahedral particles. And if you don't have the torsions in there, they start to form other crystalline structures. So the torsions are needed for the icosahedral quasicrystal in this example. But in these examples, you don't. There's enough specificity in the interactions and their geometry to cause them to form the icosahedral quasicrystals without the torsions. So with or without the torsions, we can have a 2-particle system which forms this quasicrystal. And what I should also say is, in these original simulations of Sharon Glotzer, at the kind of the point in potential parameter space where they saw these quasicrystals, they didn't always form the quasicrystals. They sometimes formed other polymorphs. In these systems, we never see any crystalline structures whatever. The only structures they form are the quasicrystals. So they're really robust in forming these quasicrystals. And the kind of last thing we want to do, can we realize these systems in any experimentally? And the obvious way actually is to use DNA origami. So if we take this 2-particle system, then the way we've tried to model them in terms of origamis is actually have a tetrahedron at the center, where the tetrahedron is not a regular tetrahedron, but one which is designed to get the correct angular geometry of these 4 patches on the system. You can see this blue one is actually kind of, this angle is at the bottom, they're quite flat at the bottom compared to normal regular tetrahedron. And then added to the tetrahedron, these 6 helix bundles at the end to give you kind of patches in those 4 directions. And then we can program the ends with sticky ends to be complementary to whichever other particles we wish. And we've just simulated these origamis in OXDNA. We've pulled them all together into this icosahedral cluster here, and they're perfectly happy in that. So hopefully we might be able to find somebody who will make these or somewhat equivalent particles and see if they can form icosahedral quasicrystals in the DNA origamis. But I think it's potentially feasible. I'm over time, so I won't tell you about these beautiful experiments with Emmanuel Levy about looking at in vivo phase diagrams of two component systems of tetramers and dimers. Dimers form the edges in this network and tetramers form the vertices in this network. And they can measure phase diagrams in vivo. But I won't mention that. But just to thank people involved in this. So Ard, I've done a lot of this work together with. Tom, Flavio, Lorenzo, John, Ben, and Peter were very much involved in the kind of generation of the OXDNA model and generating the infrastructure around that. Peter's the one who has created Oxview. He's now at Arizona State. Max did this work on, incredible work on the DNA origami systems. Marco has worked on the self-limited oligomerization, the quasicrystals, and Ava has driven the icosahedral quasicrystal, the patchy particle design process in that. She's now in Madrid, was a postdoc with me in Cambridge. And yeah, the experiments on the oligomerization done with Lawrence Lee, and Emmanuel was in the part I missed out. So thank you, and I will stop sharing my screen.
Great, yes, thank you for the great talk. I know that I'm interested in the liquid-liquid phase separation part of your talk that you didn't get to, and there's already one request from the audience. Now 2 requests, so maybe you could just...
Yeah, okay, it won't take long.
More of that, and I don't know what the audience thinks.
I can do it. I can tell you the basic story in 5 minutes. It's actually quite quick. So I'll go for that. I will just show you these this video first. This is what the experimental systems look like. So it's in yeast, and this is what happens as they grow. You can see these liquid condensates in them. You bud off a new yeast. At a certain point, they'll get the concentrations of the components will grow enough that you start a new condensate appearing in the new cells. And in the experiments, they basically measure the fluorescence in the cells with and without condensates to look at what the conditions necessary for condensation. So they're basically doing analyzing all these videos of this phase separating system. So what's the kind of what is the phase separating system? It's this. We have a protein that wants to form a tetramer, a protein which forms a dimer, an elongated dimer. So these are kind of form a vertex in our networks. The dimers form the edges in our network. As well as these proteins, they also express this IM2 domain here and this E9 domain here. And these are apparently, my biochemistry is not up to much, but these are classical pair which form a heterodimer. So that, and there's a whole series of mutations known for this system to change the binding affinity between the IM2 and the E9. So these two, because this is a tetramer, you'll have 4 of these binding domains around it. Because it's a dimer, you have 2 of these binding domains. So that's these blue and orange bits. Blue is E9, the orange is IM2. And in addition, they tag it with fluorescent proteins so they can see the tetramer and they can see the dimer. And in the system with these heterodimer domains, then the system forms these condensates where you can see that both the dimer protein and the tetramer protein are there, whereas if you don't have the interactions between them, they're just uniformly distributed in the cell. They're liquid-like. What they do is analyze all these pictures of these cells, look at the ones without any condensate in, and measure the amount, the fluorescence associated with the yellow fluorescent protein and the red fluorescent protein, and plot those as dots on this concentration plot of tetramers and dimers. But they only include those which don't have a condensate. So in the phase separating region of this phase space, you shouldn't see any points. So roughly, this looks to be here the boundary of phase separation in this system. Why you're at low concentrations, it's not phase separated because they're so dilute. If you have mismatched stoichiometry, so more dimer than tetramer, or much more tetramer than dimer, then you have these kind of imbalanced stoichiometries and you no longer phase separate. If you like, in this system where they've got much more dimers than tetramers, all the tetramers get saturated by the dimers, and then no more binding sites left, so you don't get any percolation through the system. So that's the basic physics of it. They can only measure this dilute regime, so they can't see the top of the diagram, but you expect it to kind of close at the top. They can change the interaction strength. These are our theoretical kind of predictions for this system based on this kind of coarse-grained model of the system. The shape of the diagram is not perfect, but we see the effects you expect. As you increase the affinity, you expect to drive the phase diagram down to low concentrations. And one strange feature of the results, or surprising, is they see that initially. This isn't the best phase diagram, but you can kind of see here's the phase separating region here at quite high concentrations. When you have low affinity, you increase the infinity, it goes down to lower concentrations. But if you increase the infinity even further, actually the phase separating region actually contracts and moves above the diagonal. And we think that is just because of kinetic effects, where the dynamics are coming very slow when you have really high affinities. And we actually see similar effects, somewhat similar effects, when we take a kind of patchy particle model and look at the phase behavior in the system. We're looking at them through a sedimenting system. So we're measuring this kind of the concentrations at this phase boundary, and we see a slight displacement, somewhat similar, not perfectly, to what they're seeing in experiment. But so we've done a bit of simulation as a theory, but the beautiful thing about this is not the simulations of theory, but it's the experiments. So they can really measure these two component phase diagrams in their experimental system. They can also they can also look at the cells with condensates. It wasn't reported in the paper we wrote, and try and measure the fluorescence in the cells with condensates in the condensate itself to map out the center structure as well as the from the concentrations in the condensates. Anyway, that's that story, and that's what leads to these.
Great, thank you for the super quick review of that. I guess we have a question already from the audience about the DNA origami stuff.
Yeah.
And the question is, have you done any work looking at how the chirality of DNA itself contributes to the interactions between the 6 helix bundles?
Good question. So it does minorly, and you can probably just see it in this. Okay, I guess go one back. Okay, so in this system, we're taking the ideal kind of rigid origamis with, and in this case, we've chosen the one which is meant to be straight to be perfectly straight. So this one is perfectly untwisted. So there's no chirality due to the twist of the origami. All the chirality that's there is due to the interactions between the helices, which are chiral themselves. And you can see in this system, it has a slight right-handed chirality. And if we go up to here, if you have systems with the DNA helices are right-handed, and if you have, and alpha for a DNA helix is about 30, these untwisted ones aren't achiral is because of the chiral interactions between that individual helices. But you see it's a small effect. And if we turn electrostatics on, basically it goes to 0, because when you're basically just smoothing out the chiral surface potential when you have the electrostatics on.
Makes sense.
Intriguingly, if you take persistent length pieces of DNA and put them at high concentrations, they form a left-handed cholesteric. and this is not understood in any way. I have no idea. And it's incredibly difficult to model because persistence length DNA is really, really flexible, that the methods we're using here in the DFT don't work for those systems. We have to have fairly stiff systems to apply our methods.
I have a question regarding the kind of the first part, the self-assembly with the where you had the self-limited assembly due to the frustration.
Mm-hmm.
You said that you could not simulate that in OXDNA, the equilibrium.
No, that's a pretty tough ask. We did do some non-equilibrium simulations of binding. So what we did is we pulled if we had say a 5-mer, we'd pull a new monomer in towards the system and measure the effective potential as we pulled it in at a finite rate. And so we can get kind of non-equilibrium free energy profiles, but which we know there won't be equilibrium. But what we do see is there's a barrier to binding because the domains have to displace away from the centers to be able to bind, and that's cost you free energy because you're going to entropically unlikely configuration. So those kind of non-equilibrium thermodynamic simulations is where why I said I think it's affecting the binding rate, the on rate rather than the off rate, this stress. But if you say what's the free energy for binding these systems, especially when you get to base pairing, that's a slow process, and when you're dealing with such big systems, that's going to be demanding to try and equilibrate that.
What about if you didn't do so you're saying it's too slow if you're going to try to do hybridization.
Yeah.
But what about if you were trying to do blunt end?
That might be more possible, yeah. So if I was trying to do that, what I'd do is pull things together at a slow rate and then just decrease the rate and see if the kind of free energy profiles we're getting out will becoming static. So that might be possible. But even there, you can have a kind of point where it might kind of jump to, and then you're going to have to kind of a bit of hysteresis. If you do the reverse, pull them apart. So that's the other way. If you see hysteresis, if you pull them together and pull them apart, it shows it's not fully equilibrium. So that again, it's going to be easier, but it still might not be a little bit tough to really get equilibrium. But you can do these non-equilibrium, pulling it together and pulling apart to kind of see how far away from equilibrium you are.
Okay, this is Greg again. Follow up on that question. Very interested in trying to figure out how to do things like this.
Yeah.
Would it be feasible, presumably, if you built them together? Let's say you blunt end stack them, and they stuck, and you allow them to fluctuate such that you could calculate the free energy as a function of size for pre-built structures. Is that possible? I guess in particular, trying to assess whether or not the kind of strain energy that you're growing is kind of, something you can control and design according to brick characteristics.
Yeah. So what you can certainly do is do structural characterizations of the different oligomers, or different in not just one-dimensional, kind of however they're growing in 2D or 3D, and certainly look at their fluctuations and characterize those fluctuations. That's what basically we did in this. And you can look at their energies, but energy is not a good measure of what's going on. It's really in these systems, all these origami systems and other things, you really need to measure free energies. I found, if I was thinking,
go back one slide.
If there was a signal
back one more. What about this? Can you simulate this in OXDNA?
Well, we can say, if you're saying, can I get the equilibrium between the bound and unbound state for this system?
That's what I'm saying.
Yeah, I know. If I can do the free energy of that accurately, we haven't tried to. We've been more interested in about just understanding the co-axial stacking interaction and realizing we haven't got it right. But with a lot of simulation time, I guess we might be able to.
But what's the what's the limiting thing? Why are you so hesitant?
Because so how are we going to do it? We've got to bias the system in some way, or pull it together and pull it apart, or
and why? If the free energy barrier is 3 kT, why do I have to bias it?
Why do you think it's 3 kT?
I mean, if I design it so it's 3 kT, you know?
How do you know it's 3 kT?
No, but I can.
Yeah,
but
it's so. But often
I can build it.
Yeah.
I don't know that you can build something with a barrier that's only 3 kT.
Yeah.
I find that very unlikely.
I make one Hubble hole or 2 Hubble holes or 3 Hubble holes. I vary the design.
Yeah. So
I add the poly T's. What do you mean?
Yeah. So what one can easily do is if you have a variable that varies fairly continuously and smoothly, then you can measure the free energy as a function of that variable. And so as you were bringing this to the closed state, it'd be easy to measure the free energy as a function of angle. And we do that effectively by looking at distributions of states. We could look at the distribution of this angle, but we could bias it to measure if it was quite unlikely to get to the closed state, to near the closed state. We could bias it to do that. It's when you've got a nearly closed state, binding and unbinding is going to be the slower process, where you can't just do a simple reaction coordinate, which is the angle between them. You've got to wait for the system, in some sense, to find exactly the right fit with everything fitting into each other. These things are fluctuating, and they might not fit in each other's the holes quite correctly. You need a fluctuation to a point where they can come together and they can find that binding and stay there. So we've not tried to do that exercise because we don't believe we'd get the right free energy anyway. But if one could measure that free energy and use that to parameterize our coaxial stacking interaction, that might be a useful thing to do. But I suspect with a lot of work we could probably do it, but it'd be a lot of work in terms of the timescale of the simulations. But we can do it for origamis where we're looking at more smooth structural coordinates, and we have started to do that by looking at bending origamis and things like this. So we measure free energy of bending to quite large, so that these C6 bundles rods, we've been bending them to buckling, and prior to buckling we can get the free energies out fine. But when you have two states and you're switching between them, that's when it becomes more tricky.
Are you able to put a biasing force directly in your GPU code, or you do it some other way?
We can put biasing forces in our GPU code, yeah. So typically we might do them as a function of positions of particles, or relative positions of particles, or relative positions of sets of particles. So if we have two centers of mass of two things, we can then put bias in as a function of those things, yeah. Effectively, we'll be using harmonic potentials or whatever. So we can do this in windowed ways. So if we have a harmonic potential, classical umbrella sampling with harmonic potentials with the different separations to that harmonic potential in between two parts, we can do it that way and wham it all together to get a kind of free energy landscape.
I actually
it's when you have going between two states, which are kind of discrete states.
Yeah, that's hard.
Yeah.
I actually have two questions on OXDNA as well. So one is, can you simulate something in different magnesium concentrations or different, I guess you said you couldn't measure, the difference in temperature would be difficult to kind of change in this simulation as well, but can you change magnesium? Yeah.
Temperature's easy in our simulations. Salt and type of salt is harder, basically. So we have the electrostatic interaction we put in there is a Doye type electrostatics, which is a function of ionic strength rather than specific concentration of a specific ion. And we've basically fitted the duplex thermodynamics as a function of that ionic strength to thermodynamics of melting, of hybridization as a function of sodium chloride concentration.
So in DNA origami, people usually put in magnesium chloride inside, and I mean, something that I've been looking at recently is like if you change the concentration of magnesium, probably the interhelical spacing and like the helical rise changes as a parameter of.
Yeah. So yeah, what is true though, probably when you get to fairly large concentrations of salt or magnesium, then the systems were strongly screened and they don't change so much. So, and the other thing I should say, the thermodynamics of hybridization and it's dependent on magnesium compared to salt is very strange. Because if you just think it's just behaving like a dihelical electrolyte, then magnesium chloride will have the ionic strength 3 times that of a sodium. But in terms of the effect on the thermodynamics, it's a factor of 50 or whatever. So there's clearly some complex electrostatics going on, which is what's going on with magnesium. What we basically do is in our origami simulations, usually do them at 1 molar salt and say that's roughly equivalent to the kind of magnesium conditions we're seeing because it's at high ionic strength and everything's pretty well screened. That's our kind of default. But yeah, in terms of saying when this particular concentration or ionic strength in our model maps onto this in reality is a hard one. And they're probably going to be multiple mappings depending on what properties you look at in some sense. So we've got the map, we've done the mapping so it lines with the thermodynamics of hybridization with salt, but other things we know it doesn't align. So one of the lucky features actually in OXDNA is if you take a 4 helix junction, the stacking, it probably overstacks compared to what you expect for sodium. So sodium, you can have the stacked or open forms of the four-way junctions, and you have to go up to quite high salt concentrations to get it to stack. But our system stacks more easily than that, and that is actually a bit more like magnesium than salt. So in terms of the junctions, four-way junctions at our high ionic strengths, they're more behaving like magnesium than salt, and so that's pretty helpful for the origami simulations actually. So if you might be aware, although most people use magnesium, Hendrik did some work where he assembled origamis in salt, and they had to go to pretty high salt concentrations. I think even perhaps 5 molar salt to get things to assemble. And this is probably because the four-way junctions are less happy being stacked in salt than they are in magnesium.
I see. Thanks.
So that's a long answer, but electrostatics aren't easy, and yeah.
All right, thanks. And another question is, I heard from Alexei Aksmentiev's talk that OXDNA are better for simulating single-stranded DNAs. And I'm interested in understanding why that is.
That's kind of him compared to what? All atom.
Oh, okay.
What was the comparison? It's better, OXDNA is good for single strand compared to what other model?
I mean, so I wasn't really sure what he was what he was trying to say there. But
he might have meant his kind of energy MD, where he does kind of pseudo all atom, where he doesn't have the waters in, or he might have meant his what's it called, MRDNA or Mr. DNA, where he's got this coarse grain model. I think in MRDNA, I'd have to check. But so in our designing of the model, we've tried to get single-stranded properties pretty accurately, as well as double-stranded properties. So that's the kind of, and the reason for that is because we want to get the thermodynamics hybridization correctly. You need to not only model the duplex correctly, but the single strands correctly, and have the right amount of entropy in the single strands to get that transition correctly. So and that means also that we've got the entropic elasticity of single-stranded DNA reasonably well. So if you look at force extension curves of single-stranded DNA, that's reasonable. So if you have an origami where you have a kind of single-stranded bit joining two things and it's acting like a spring, then OXDNA can capture the effects of that kind of entropic spring fairly well.
I see. Thank you so much.
Yeah.
We have another question from the audience that I will ask you.
I gotta leave. Thank you, John.
Yeah, no problem. So I'm talking too much.
I also have to go. That was awesome, John. Thanks.
Yeah.
So the question is, can you reiterate how the information you gained from studying DNA twist and handedness helped model particle assembly?
Say that again, sorry.
It's about connecting the sort of small length scale twist of DNA to and handedness to particle assembly. So can you reiterate how the information you gained from studying DNA twist and handedness helped model particle assembly?
So if we're saying, can I try to explain this slide again? Which is probably, so this is quite subtle in some sense. So what's happening is because you've got internal stresses in your origami, these are causing it to fluctuate in a chiral manner. And what I've tried to explain is why the chirality of the fluctuations, that they basically adopt a shape which is like a helix, why that has the opposite handedness to their internal twist, the twist of the actual particles. So it's a little bit confusing because you've got the twist of the duplexes in the origami, you've got the twist of the origami, and you've got the handedness of the writhe fluctuations. So writhing is just another word for the shape fluctuations and whether they are have a chirality to them. And it's basically in this kind of this table, what we're seeing is the writhe fluctuations are the same sign as the internal stresses in the individual duplexes. So if the duplexes are over twisted and have a kind of right twist compared to their equilibrium twist, then they want to get rid of some of that twist, so they can get rid of some of that twist to writhe whilst keeping the linking number roughly constant, which is, although in our systems isn't a topological environment, it can be in a closed system. We're probably in some intermediate kind of system where it's constrained by the junctions, but not fully a topological invariant. And so what we're basically seeing is that the writhe fluctuations are the same sign as the internal twist in the duplexes. And you see when you go to this rigid rod-like structure to the ensemble structure, you see that individual over twist in these structures decreases and it transfers some of that to writhe. So you're seeing that happening, that transfer of the twist stress into writhe fluctuations. And why it wants to do that is just it's always better to spread the stress across different modes rather than have it in one mode. Because if you have a quadratic, larger stresses will give you higher energies, rather than if you can spread that across different modes of deformation, it costs you less. So it costs you to bend the structure to form these writhe helical configurations, but the cost of the bending is offset by the reduction in the twist stress in the individual helices.
Thank you.
It is quite subtle. It took us quite a while to figure it out. I actually played with kind of, I will just stop sharing my screen, one moment.
Is this the telephone cord?
No, it's some rubber tubing where I've put them together with some twist stress some stress in there, and so this is a 4 helix bundle, and it naturally wants to twist. But you can also look at what happens if you writhe it one way or the other as well.
Yeah, so I mean, this is a crazy question. Maybe people don't get this because you designed origami normally, so this doesn't happen. But can you envision sort of like forcing sort of a twisted thing such that the DNA actually melts in a way that you want, so you have like a responsive particle where it's, you know, right? Like you can engineer braking internally for that purpose.
So yeah, melting in particles with stress in will be at lower temperature than melting in particles without stress in. Then what I think you're trying to say is, can you perhaps cause melting to be localized to a certain spot because you're putting particular stress on?
Right, exactly. Yeah.
And so I'm sure that's perfectly feasible. If you took one of these origamis and put a lot of bend stress or twist stress in a certain place, that would probably be the hardest part to form. And also, if you form it and then raise the temperature, then that's going to be the first part where the strands are going to fall off and melt. So if you wanted to control the melting, then you can do it with these internal stresses. They're less stable. if they've got internal stresses. And that could be quite localized because you can add these extra bases at certain junctures quite locally. I think one of the things Vonimir tried to do, as well as these twisted rods, he tried to do sort of bent particles which had a kind of V bend in them. And I think he struggled to assemble them, probably because the bend stress at that kink was too high, and so they were struggling to assemble as it happened. But you can control the stresses to affect melting, to affect structure, and to affect mechanics as well.
But if I understood, but I don't really know anything about this stuff, your OXDNA can't really capture the coupling between the twist and stretch directly, right?
Yeah. So yeah, we can capture coupling between different types of modes of deformation. That's a nice thing in some sense. We see things. You can create kind of little theories and models if you just got one deformation mode or two deformation mode. But in the SWOT simulations have all the deformation modes in there. What we haven't got perfectly is actually just the extension modulus is too large. So, but we have potentially got the couplings between them. There is actually a twist stretch coupling, which is quite subtle, right, and we don't get the right sign for that. I think RNA and DNA, they're different signs, but there is also a twist bend coupling, and we do get that, and that comes out from the asymmetry of the helix.
Okay, thank you. I guess my questions have scared everyone away. You had
I have a question, last question maybe. You have mentioned that when you measured the stiffness, like for a 6-helix bundle, then there came a large difference. Okay, now have you, I'm just curious that have you tried for a square lattice, like for square bricks?
Yeah, so I just showed you numbers for 6-helix bundles. We've done them for 4-helix bundles and other kind of structures. So that overestimation compared to experiments is pretty universal compared. But the two things are the experiment measurements are quite hard to do, and I do think assembly quality will affect the experimental numbers, as well as this problem with the OXDNA stretch modulus. So in one of the papers, it was by, I think, Tim Liedl's group and others, they made some very long rods, not with origamis, but with just single strands, which could go much longer than the origamis. And they looked at persistence lengths of individual rods, and they saw quite a bit of variability between individual rods. So they had got estimates of the persistence length of an individual rod, and they had an error in that. And that error was smaller than the differences between the different rods they looked at. So that's suggesting actually the ensemble of structures in the experiments was heterogeneous, not homogeneous. Whereas we're just looking at one rod and it's always a perfect one. So you would expect, if we're gonna, even if we had a perfect model, we'd always expect our numbers to be higher than an imperfect rod. But if they manage to assemble the rods perfectly and OXDNA was perfect, you would expect agreement. So it's hard to estimate what the effect of potential heterogeneities are. And there's not just assembly defects, there's also defects in synthesis in your strands as well. So that's hard to kind of quantify the effects of those things.
Thank you.
Yeah, thank you very much, John. I wish, if this wasn't COVID, we'd be having beer and pizza right now.
Yeah.
But
I'll go home and have a beer, not pizza. It's a bit late for pizza now.
Yeah, right. Well, hopefully we'll see you in Boston at some point.
Yeah, that'd be cool. Yeah, good. So thanks for the invitation. And if anybody's got questions about OXDNA or anything or this kind of stuff, then Henry can just buzz me a line.
Sounds good. Thank you very much again.
Yeah.
Thank you, John.
See ya.
Sleep well.